We'll get into a special kind of a motion today. For a particle that wants to be at a certain position, and when you displace it from that position, there are compelling forces that would want to bring it back to that position. Which means, let's say, there is a point O. Let's say there is a point O where you find a particle of mass m, and the particle is subject to forces such that any attempt to displace the particle to a point P, if you attempt to displace the particle to the right of O, that means at a point P, then there is going to be a force that would want to bring the particle back to O. This force is a restoring force. If you displace it to the left of O, that means at this point call it P prime, then the force would act to the right. This again would be referred to as a restoring force. Right. So we would look at characterization of such forces which are restoring in nature, restoring in property, and the further you displace the particle from O, the greater is the magnitude of this force. The further you displace the particle from O, greater is the magnitude of the force, which means if you have displaced it by an amount x to the right, on displacing it by an amount x to the right, the force acting on the particle towards O, attempting to restore the position of the particle, would be kx in magnitude. The restoring force would be proportional to how far the particle is from O. Right? Now, if I have to algebraically describe such a force, let me call this as O as the origin. Not that it will make a difference. And let me choose to call this as the positive direction of the x-axis. Then the force, the restoring force, would be characterized algebraically by a constant k into x appended with a minus sign. Now what would this minus sign do? If x is positive, that is for the point P, kx with a minus sign will be a negative number, k is a positive constant. This k we will refer to as a force constant. If x is positive, then minus kx would be negative. F being negative means F is directed leftwards, because everything rightwards is chosen positive, leftwards from O is chosen negative. So then, if x is positive, F is negative, means it's directed towards O, leftwards, this way. If I look at the x of this point P prime, the x of this is negative. So when x is negative, F becomes positive. That means positive means directed rightwards and directed towards O. So a description of this nature would cause the force to be restoring in character, the magnitude of the force increasing with x, or magnitude of x, as the magnitude of x, which reflects on how far the particle is from O, right? Magnitude of x, mod x, which reflects how far the particle is from O, will measure the magnitude of the force which is restoring in character, right? So let's try and understand how a particle will respond to the action of such a force. This again a force field. This is a force field because for different values of x you have different values of force acting on the particle. So we might want to associate what's referred to as a one-dimensional force field. Force field in the x direction to which the particle is subject. Right? Now even before I get very mathematical about it, let me first qualitatively understand and make you understand what happens when a particle is under the influence of such a force field. Okay? And even before I proceed, let me also mention to you that this force field, one-dimensional force field, will be conservative in character. We would look at the motion of the particle under the influence of a conservative force field, F equal to minus kx. That means with this force field, we would want to associate another entity for the particle, which is the potential energy, right? With the conservative force field, we are always eligible to attach and append potential energy, right? But that later. Very qualitatively, let's examine what the particle does when subject to this kind of a force description. Okay? Say, at a certain instant of time, the particle is at O, and at this instant, the force acting on the particle is 0, because its distance from O is 0, right? But let's say I impart an impulse to the particle rightwards. An impulse acting on the particle will cause a velocity to build up in the particle, right? A change in linear momentum is brought about. Let's say the particle is then acted upon by a force. The particle then builds up a velocity v naught at this position O. Now at this position, again, the particle is in equilibrium because the force acting on it is 0, right? So we will call this the equilibrium position and sometimes also the mean position, because the net of all forces acting on the particle at O is 0, right? Force at x equal to O is 0, and this O therefore would be referred to as an equilibrium position. Or mean position. Equilibrium position or mean position. Now, the particle, even though is acted upon by 0 force at x equal to 0, because of inertia, it would move to the right. It would move to the right, right? Now, the moment it starts moving to the right, it's going to be pulled back. There would be an attempt to pull the particle back to O because of this force. This force would therefore want to retard the particle. The particle will then get retarded, and therefore its velocity will start depleting. Right? The particle, in any case, moves to the right at some x from O. It develops a velocity v, which is less than v naught, because the particle has been retarded from O to P. The particle has been retarded, right? Not only that, at any given x, the magnitude, the acceleration on the particle would be force divided by the mass of the particle, which would be minus k by m into x. That's the acceleration on the particle. Now, in this case, it's retardation. Do you realize? Because it's leftwards. If x is positive, a is leftwards. Therefore, the particle is retarded, and the magnitude of the retardation grows with x. As x grows, the magnitude of a will grow, right? Therefore, the particle starts to lose velocity faster and faster and faster, right? That means if in the first second it has lost 1 meter per second, then in the next second it'll lose more than 1 meter per second. Then in the third second it'll lose more than what it lost in the second second, right? It'll lose velocity faster and faster. Why? Because it's being retarded more and more as it's moving further and further away from O. Yes or no? Right. So then eventually the particle arrives at a point S. The particle arrives at a point S, and it would have lost all its velocity by then. It would have lost all its velocity by then, right? So the velocity of the particle then at S becomes 0. But the acceleration is not 0. Acceleration is very large. Acceleration is, or the retardation, in this case now it will be accelerated, will be proportional to the length OS, which is more than any other length between O and S. So the acceleration would be the largest it could be at S, right? So the particle will not move further to the right. It will now start to move to the left under the influence of a leftward acceleration. Under the influence of a leftward acceleration, kx, k into OS in this case, it will start moving leftwards, right? So this was the rightward bound of the particle. This S is the rightward bound of the particle from O. It will not go beyond S to the right of O, right? Now, it starts to come back. It starts to come back. Now when it starts to come back, realize that the force is acting always towards O. Therefore, the particle will begin to accelerate. The particle will begin to accelerate. So the particle accelerates from S to O. The particle accelerates. What happens to the magnitude of the acceleration? It decreases because distance from O is decreasing. So the magnitude of acceleration will decrease. So even though it's gaining velocity leftwards, but it's gaining at a smaller and smaller rate. That means if in the first second it has gained 2 meters per second, then perhaps in the next second it might have gained only 1 meter per second. Why? Because the acceleration is decreasing in magnitude. Got me? Yes or no? Yes, so then the particle begins to accelerate from S, and its velocity keeps growing because it's accelerating. Even though it will grow at a smaller and smaller rate, it will still grow, right? By the time the particle reaches O, it's the same position that we are talking of, and therefore we are talking of the same potential energy of the particle, because, right, conservative force field, with every point you associate a potential energy, and therefore by the time it reaches O, we expect the particle to have the same speed, same kinetic energy as it had at O earlier, right? For a given position, we'll be talking of the same potential energy. So by the time it arrives at O, it has the same potential energy as it had when it started from O. And therefore, to preserve the total mechanical energy, it will have the same kinetic energy at O. That means now its speed will still be V naught, except that the direction of the velocity would be V naught leftwards, right? Now the particle starts to move to the left of O, and the retarding force will act to the right, which, like before, will keep decreasing the velocity of the particle at a faster and faster rate. Why? Because the distance from O is growing, therefore the magnitude of retardation is growing, so it will keep losing velocity at a more and more rapid rate, right? So you would expect at a certain point R, once again, the velocity to become 0. Right? And then the particle is incapable of going further to the left of R. So this is the leftward limit of the motion of the particle, right? The particle then, from this point onwards, it's acted upon by a force to the right, so it will accelerate rightwards. When it accelerates rightwards, its velocity will grow, and the acceleration will decrease. Why would the acceleration decrease? Is because distance from O is decreasing. Therefore, even though the velocity is growing, it's growing at a smaller and smaller rate. And then it comes back to O with the velocity V naught to the right, and then undertakes this journey again and again, time and again. If there are no forces that would compel the particle to lose its total energy, if it's under the influence of just this force, and no force that is going to eat up or hog up the energy of the particle, then the particle would continue this motion identically between R and S forever, right? The motion is therefore bounded. Do you realize that the motion is bounded? Because Its limits are R and S. Give me some time. Let me also teach now. I know you know everything, but now, one thing, when the particle went from O to S, right, it was subject to forces that were proportional to how far the particle was from O, had a starting velocity v naught. After having traveled a length a, OS equal to a, after having traversed a length a to the right of O, the particle would have lost all its velocity, right? So when it reaches S, its coordinates are a0. Clear? Now, realize that the journey it exhibited from O to S, the forces that it experienced from O to S in character, proportional to how far from O and restoring always, it experiences the same situation when it traversed from O to R. It experienced forces that were proportional to how far it was from O and were directed towards O. So whatever it did to the right of O, now it would demonstrate to the left of O. Exactly the same motion will get replicated, but in the opposite direction, right? And therefore you would expect, if the particle had traveled a distance a units to the right of O to lose all its velocity, it would now travel a distance a units to the left of O to once again lose all its velocity. Therefore, if this point has coordinates a0, if this length is a units, this length will also be a units, and the coordinates of this particle at R would be minus a0. So the motion is bounded, confined between limits minus a0 to plus a0, right? Halfway between these 2 points is the equilibrium position. Halfway between these 2 extreme limits is the equilibrium position, or the mean position, where the net of all forces acting on the particle is 0, right? Now this A, its maximum distance from the equilibrium position, is also called the amplitude of motion. This is called the amplitude of motion. The particle continues to move back and forth, back and forth, back and forth. The motion is therefore oscillatory in character. The motion therefore is not only bounded, it's also oscillatory in character. It's oscillatory. It'll oscillate between R and S, right? Now, conventionally, this motion, when characterized by this kind of a force, is called simple harmonic motion. This motion is called simple harmonic motion. Or SHM. Right? Now, if a particle is executing SHM between limits R, which is minus a0, to S, which is a0, with, let's say, this being the mean position, O being the mean position or equilibrium position, then we define a very important entity for this motion. Let's say at a certain instant the particle is at P. At a certain instant the particle is at P and is moving to the right, and is moving to the right. Now the particle goes to its rightmost extremity. The particle goes to its rightmost extremity and then turns around, comes to the equilibrium position, then traverses to the leftmost extremity, and then turns around and comes back to P. It started from P and came back to P, right? Now, while it did this, every point between R and S was covered at 2 instants of time. See, notice that every point between the limits R and S was covered at 2 instants of time during this journey, during this cycle. But you might say, hey, R and S are covered at only 1 instant of time. During this cycle, see, S is covered only at 1 instant, and it seems that R is covered at 1 instant. This might seem paradoxical. No, even R and S are covered at 2 instants of time. They are coincident instants of time. All other points between R and S, for example, a point O is covered at 2 distinct instants of time, but the extremities are covered mathematically at 2 coincident instants of time. That's the way we'll look at things. That's the way we'll examine the whole game, right? So essentially, in this full cycle, this is a full cycle of motion. Starting from any point P, coming back to P, covering every point exactly twice, is a full cycle of oscillation. Is a full cycle of oscillation. This is a full cycle of oscillation. That means PSRP, PSRP, PSRP. That's a full cycle, right? A full cycle, a complete revolution, or a complete oscillation, or a complete oscillation. And the time taken to execute one full cycle is called the time period of motion. The time taken for a full cycle is time period T. Of the motion, time period T of the motion. Down the line, we'll be able to establish that it didn't matter where this point P is. It could have been here, it could have been here, it could have been here, it could have been there. The time for a full cycle defined in this manner will be the same and will not depend on what I choose as the starting point of the motion. This T, capital T, will not depend on where P is located, as long as you make sure that the particle has come back to P, making sure that every point between the extremities is covered exactly twice. A full cycle is established. Now, in 1 second, if it takes T seconds for a full cycle, then the number of cycles in a given second would be 1 by T. Yes or no? Right? So then number of full cycles per second is going to be 1 by T, and is called the frequency of oscillation. Is called the frequency N of oscillation. The units is obviously per second or hertz. Per second or hertz. Right? Number of cycles per second would be the frequency of this oscillator, N. Right? Now, so far so good, right? You understand things here. Yes, we will see very shortly. Many places, I'll show you in a short while, not just pendulum. If there is a mass attached to one end of the spring, and the spring is compressed and let go, then that particle will exhibit this kind of motion. If a particle is floating on water, partially immersed, partially above water, and you slowly submerge it and let it go, then it will exhibit SHM. So, umpteen cases of this oscillation, right? Yes, it will increase. Yes. What he's saying is, we gave it an impulse at O. That means we gave it a certain amount of kinetic energy at O, right? And the particle went all the way to S. If it gave it more kinetic energy, then it's capable of traveling a further distance before losing all its velocity because it had more velocity. So it'll take longer to lose all its velocity. It'll travel a greater distance, I mean, to lose all its velocity, isn't it? Right. So then A will increase. Then A will increase. If V naught was more, then A would be more. Yes, absolutely. Now, let me start with the energy implications. Let me start with the energy implications of this motion, right? So with this motion, like I said, this F is a conservative force, one-dimensional conservative force, and we can always associate potential energy with this kind of a force, therefore, right? This is O. Let's say at some instant of time the particle is at x, right? And is moving to the right. At some instant of time the particle is at s and is moving to the right. In a small time dt, the particle comes to q, having got displaced by an amount dx to the right. The particle has got displaced by an amount dx to the right. Infinitesimally small displacement dx to the right. Now, for this very small amount of displacement, the force acting on the particle is practically the force that it was being acted upon at x. At x, the particle was being acted upon by a force kx directed always towards O, because it's a restoring force. That's the kind of force we are characterizing, right? Now, what is the work done by this force, by the conservative force? What's the conservative force? This kx acting towards O always is the conservative force. What's the work done by this force when the particle goes from? Yes, angle between force and displacement is 180 degrees. Therefore, the work done by the conservative force, work done by the force of the field. So we say work done by the field, right? This is a one-dimensional force field. Work done by the forces of the field then would be minus kx into dx, right? And like I had discussed during our digressions on work, power, energy, the work done by the forces of the field will be negative of the change in potential energy of the particle, would be negative of the change in potential energy of the particle. That's how potential energy was defined, right? So when the particle goes from P to Q, the change in potential energy du would be negative of the work done by the field. That was the change in potential energy of the particle, negative of the work done by the forces of the field, right? That's how potential energy was defined, right? And which then would be kx into dx. Clear? So the change in potential energy is kx into dx when the particle goes from P to Q. In general, let's say when the particle goes from x equal to 0 to x equal to x, when the particle goes from x equal to 0 to x equal to x, the total change in potential energy would be the potential energy at x minus potential energy at 0. X runs from 0 to x. That would be the change in potential energy. Potential energy at x minus potential energy at 0. That is when x runs from 0 to x. That's the change in potential energy of the particle between 0 to x, right? Which then, as you can see, is half kx squared, right? Now, that's the potential energy at x minus potential energy at 0. Now, like I told you, it will not make too much of a difference if we choose a reference point where our choice of potential energy would be 0. So, no loss of generality, no loss of physicality if I choose to call potential energy at the mean position. This is potential energy at the mean position to be 0. It's fine, right? So when I do that, if I choose u0 as 0, then I end up getting potential energy at x of the particle as half kx squared. Right? Now very clearly, there is some symmetry exhibited in this potential energy. Potential energy at x is the same as potential energy at minus x, as you can see, half kx squared. That means if the particle is 2 centimeters to the right of O, or the particle is 2 centimeters to the left of O, it's going to have the same potential energy, right? Also, potential energy is going to be maximum when x is maximum. When x is x max, what is the maximum value of A? X? The amplitude A. The maximum x is the amplitude of motion A. Therefore, u max is half Ka squared. Is half Ka squared. And that happens at the extreme S where x is A. And also at R where x is minus A. At these 2 points, the potential energy is a maximum and is half Ka squared. Now at these 2 extreme positions, the velocity has become 0. Therefore at these points, kinetic energy is 0. What's the total energy at S? TME, total mechanical energy at S or R. Kinetic energy 0, potential energy half Ka squared. That means half Ka squared. That's a total mechanical energy at the extreme positions. And the total mechanical energy at the extreme position would be the total mechanical energy anywhere else. Yes or no? That means if the sum total of kinetic and potential is half Ka squared here, then at this point also it's going to be half Ka squared. Then at this point also it's going to be half Ka squared. At this point also half Ka squared. That means it's half Ka squared anywhere else. The only difference is that at the extreme positions, this half Ka squared is completely confined to potential energy. Anywhere else, this half Ka squared partially manifests as kinetic energy, partially as potential energy. So half Ka squared shuttles between the 2 entities, potential and kinetic. At different positions, the only difference would be the manner in which potential and kinetic energy get delegated. Their sum total will remain half Ka squared, right? So the total mechanical energy not only at S or R but any other point would be half Ka squared. So we say the energy of oscillation. We say the energy of oscillation is half Ka squared. The total energy of oscillation, so to say, is half Ka squared and is proportional to the square of the amplitude. Is proportional to the square of the amplitude, right? So if by some means the amplitude gets doubled, then the total mechanical energy of the oscillator will become 4 times, right? Now, so far so good, simple, right? Now, at O, right? At some point P, x0, let's say the speed of the particle was v. Speed of the particle was v at some x0, right? Then what's the total and let's say for this motion A is the amplitude. A is the amplitude for this oscillator. The total mechanical energy TME will always be half Ka squared. Would always be half Ka squared, right? At P, therefore, the total mechanical energy would be half Ka squared. which is partially appearing as, which partially is manifested as kinetic half mv square plus potential, which is half kx square. Yes or no?
Yes, sir.
Right? Now, we could therefore have said v square is k by m into a squared minus x squared. See? Half getting cancelled, dividing by m. Then if I solve for v squared, this is what transpires. Now v squared is always greater than or equal to 0. V squared is always greater than or equal to 0. So this must also be greater than or equal to 0. K is a positive constant, m is a positive constant. Now, therefore, in order that this is greater than or equal to 0, we must have a squared minus x squared always greater than or equal to 0. That means x squared less than or equal to a squared. That means x always lies between minus a to plus a. That means mod x will always be less than or equal to a. Right? Which is very clearly reflected in this. Very clearly reflected in this. Got me? You know? Now, let me choose to call this entity k, force constant k, divided by m. It's a positive number because k, the force constant, is positive, m, the mass of the particle, is positive. So in order that its positivity is reflected in its expression, let me call this as some omega square. Let me just algebraically call this as some omega square. Clear? K by m, let me refer to that as omega squared. The physicality of omega squared we will figure out when the time is right. But for the time being, let me just look upon this as a mere algebraic entity. Okay? Then the speed of the particle v, if you plug in k by m as omega squared, v then would be omega root a squared minus x squared. Right? Hey, but v at this instant would be dx dt. V at this instant is going to be dx dt. So this is going to be dx dt. Right? This I could have further written as dx by root a squared minus x squared as omega dt. Right? If I integrate both sides, then this integral is actually sine inverse x by a. Integral 1 by root a squared minus x squared is sine inverse x by a. Omega will come out, so it will be omega t plus a constant of integration. Right? So we get like a sine inverse x by a as this integral is omega t plus a constant of integration phi, plus a constant of integration phi. Constant of integration for the time being, we'll call this just a mathematical constant. If there is any physicality associated with it, we'll examine that down the line. Okay, but for the time being, just a mathematical constant phi, a constant of integration. This constant of integration customarily is referred to as a phase constant. Yet you will have some constant. So this would give me x is a sine omega t plus phi. So the displacement of the particle from the mean position gives me x. It could be positive, 0, negative, a, minus a, right? So this is displacement of the particle from the mean position from the mean position at various instants of time t. Again, you see the right hand side would always lie between plus minus a, isn't it? Because the maximum value of sine would be plus 1, the minimum value of sine would be minus 1. So x max would be plus a, x min would be minus a. At every step it reminds you that the motion is bounded, right? Confined between limits minus a to plus a. Now, see, the important thing is that, you know, this entire motion was f equal to minus kx, described by this, right, where f was m into acceleration, which is d2x dt2. Henceforth, you know, x dot would mean dx dt, whereas x double dot would mean d2x dt2. X double dot would mean d2x dt2. This is the velocity and this is the acceleration. X dot is the velocity v and this is the acceleration a. X double dot would actually mean the second derivative of x with respect to time. X dot means the first derivative of x with respect to time, the velocity. This would be the acceleration, right? So force is mass into acceleration, d2x dt2, right, which is minus kx, right, which means x double dot, the acceleration, x double dot is minus k by m. This is x double dot is minus k by m into x, right? So the acceleration is minus omega squared into x. That's the acceleration as a function of x. That's the acceleration of the particle. Every time you find that acceleration is minus some omega squared minus a positive number into x, you can conclude that the motion is simple harmonic. Every time you find that the acceleration is proportional to x with a minus sign like this, with this being a positive constant, you can conclude the motion is simple harmonic, right? In fact, the acceleration as a function of x, is given like this. If you have to plot acceleration as a function of x, then it's going to be a straight line with slope minus omega squared, negative slope, and passing through the origin, right? Y equal to mx. M is negative, m is minus omega squared. So do you realize that it's going to be a straight line like this? This is between minus a to plus a, between x equal to minus a to plus a. That's a variation of acceleration with x. Variation of acceleration with x, right? At x equal to plus a, the acceleration is minus omega squared a. At x equal to plus a, the acceleration is at a is minus omega squared a. Minus omega squared a means directed towards the origin, that means leftwards. See, if this was the motion, this was O, this was x equal to a, then the magnitude of acceleration at a would be omega squared a to the left towards O, right? When the particle is at minus a, when you plug in x equal to minus a, acceleration would be positive. So plus omega squared a, therefore plus omega squared a is omega squared a directed towards the right, right? Which means at minus a, the acceleration is omega squared a, and at plus a, it's minus omega squared a. That's the acceleration. Do you realize that the maximum acceleration in magnitude would be omega squared a? A max therefore would be omega squared a. And where does it happen? It happens at the extreme positions, at the amplitude positions. You get maximum acceleration of the particle, right? Also, notice v, the speed of the particle at any given instant as we obtained was omega root a squared minus x squared. V is omega root a squared minus x squared. As x increases, v will decrease, right? So v will be maximum when x is 0. As x increases, v will decrease, right? So for the smallest x, which is at x equal to 0, v would be v max, and it's going to be omega a. Maximum velocity would be at the mean position and will be omega a. That means at the mean position, the velocity of the particle will be maximum. This v naught will be omega a at the mean position, right? In fact, the speed versus x. Can I wipe this portion off? The v versus x, let me tell you, if I had to plot this, may not be able to give you insight in it right now because we have not done ellipses, but let me tell you that it's going to be an ellipse like this. Between minus a to plus a, it's going to be an ellipse. It would be an elliptic shape between minus a to plus a. Speed versus x is going to be elliptic in shape. At x equal to a, it's going to be 0. At x equal to minus a, it's going to be 0. At x equal to 0, the mean position, it's going to be of magnitude omega a. That's the speed versus x characterization, right? That's tricky. Now, if I differentiate this with respect to time, this is x versus time for the oscillator. If I differentiate this with respect to time, I get the velocity v, which is omega a cos omega t plus phi. Omega a cos omega t plus phi. It's going to be, and again you can see that maximum v would be omega a, because this would be the maximum value of cos would be plus 1, so v max would be omega a, right? Now if I acceleration would be what? X double dot, x double dot. Differentiate this again with respect to time. If you differentiate this again with respect to time, you get minus omega squared a sine omega t plus phi. Yes or no? Hey, but a sine omega t plus phi, a sine omega t plus phi is x. So you can see that it's minus omega squared x acceleration, which is what you, so every time you get a equal to minus omega squared x into x, you can conclude that the motion is simple harmonic, right? In fact, can I wipe this off? Huh? Differentiate x with respect to time, x dot. So omega a cos omega t plus phi. I'll come to that. Don't, no, koi zaruri nahi hai, not necessary. Any other point I could take, but give me some time to tell you all of it, right? In fact, at any given x, the potential energy is half kx squared. At any given x, the kinetic energy is half mv squared, which is half m. V squared is omega squared into a squared minus x squared, right? V is omega root a squared minus x squared, right? So m omega squared, see, omega squared is k by m. So this is like half k a squared minus x squared. Once we learn parabola, we'll be able to feel more convinced about the plot of u versus x. Say in the y direction, I could have plotted u as well as kinetic energy. Potential energy varies this way. Between minus a to plus a, it's going to be parabolic. That's a variation of potential energy with x. That's a variation of potential energy with x. And kinetic energy between minus a to plus a would vary like this. This dotted structure would represent the kinetic energy versus x. The potential energy is going to be an upward opening parabola. The kinetic energy is going to be a downward opening parabola. right? This is how u and k vary with x. One opens upwards, the other opens downwards. Stop. ठीक है. Now, so far so good, right? Stand by one.